This is the fifth how-to tutorial for CHM1011. In this tutorial, we're going to be looking at the different shapes and orientations of atomic orbitals. What exactly is an atomic orbital? I think this is something that is often a point of confusion for people studying chemistry for the first time. An atomic orbital is defined as a solution to the Schrödinger equation. And it's defined by quantum numbers: n, the principal quantum number; l, the angular momentum quantum number; and ml, the magnetic quantum number. It's important to acknowledge and to try and grasp and understand that an orbital is a mathematical function. It's not a region of space. Okay? It's not a physical entity. It's a mathematical function which describes the probability of where you will find an electron. An orbital can exist over all space. It's not explicitly defined by some of the shapes that you'll see. For example, the radial component of a 1s orbital is 2e to the power of minus r. Okay? The solution is non-zero. No matter what value of r you choose, that is, no matter how far from the nucleus you are. This is a bit of a strange point. I mean, what I'm really saying to you is that take a simple example such as a hydrogen atom, there's a non-zero probability. In other words, there is some probability that the electron exists a fraction of a centimeter from the nucleus. There's also a fraction of a possibility that that electron exists a kilometer from that hydrogen atom's nucleus. The reality is that that probability is very, very small, but it is not zero. Obviously, as one's getting further and further away from the nucleus, the probability of finding that electron is smaller and smaller. So we usually describe the shape of an orbital by where an electron is likely to be found around 95% of the time. Each orbital has a unique shape with respect to the x, y, and z axes. Okay, on this slide you can see a couple of examples, and these are d orbitals. The orbitals that you should be familiar with as a part of Chem 1011 are s, p, and d orbitals. S orbitals are the simplest of these three. They have a spherical shape. The probability density changes uniformly moving away from the origin. As you can see, the radius of these s orbitals increases as you go from 1s to 2s to 3s and so on. P orbitals have what is often called a dumbbell shape, and these can have three orientations along the x, y, or z axes. And as you can see, these dumbbells are aligned along the three axes, and that's where they get their names from. So that px, in this case in the figure, the 2px atomic orbital is aligned along the x-axis. That is, it's like a shish kebab with the x-axis going through the two lobes of the dumbbell. The py atomic orbital has the y-axis going symmetrically through the dumbbell, and the pz axis has the pz orbital has the z-axis going through the dumbbell lobes. There are 5 d orbitals, and they have the shapes and orientations that you can see here. In the case of the 3dxy atomic orbital, it gets its name from the fact that it has these nodal planes. In other words, these are planes where there is zero probability of finding the electron, that runs along the zx and zy planes. Or you can say that the lobes are in the xy plane, and that's where this orbital gets its name from. In the 3dxz figure, you can see that the lobes exist in the xz plane, and you have nodal planes in the ZY plane and also in the XY plane, and so on for DYZ. The 3D x squared minus y squared orbital is slightly different to the first three in that the x-axis and the y-axis go symmetrically through the lobes. Finally, the 3D z squared orbital has a more odd shaped. I think of it as a dumbbell with a donut going around it, and the dumbbell is aligned along the z-axis while the donut is on the xy axis. The planes and the conical plane that you can see in that fifth example are called nodal planes. And a reminder that nodal plane is a region where you will never ever find the electron. There is a 0 probability of finding the electron in that place. Going back to the s orbitals, we can also see that there are nodal regions for the s orbitals. This is not so much in a plane, but in a spherical shape, a bit like a shell, if you like to think of it that way. Perhaps like, or the layers of an onion. Okay, in between each of those layers, where you have a non-zero probability of finding the electron, you have this shell where there is a 0 probability amplitude for finding the electron. In other words, you will never find the electron there. One of the weird things about quantum chemistry is that an electron can actually go from one region through a node to the other region, but that mathematically speaking, the electron can never ever be at the spot where the node exists. There's a phenomenon called tunneling, which allows the electron to go from one non-zero probability region to a neighboring non-zero probability region. And just revising the nodal planes that we saw with both p and d atomic orbitals. Nodal plane represents a plane about which the wave function for a particular orbital has 0 probability amplitude. So in the p orbital case, we can see that there is one nodal plane, and in the d orbital we can see that there are 2 nodal planes.